Okay, welcome back. The last video we ended talking about interneurons, and now we're going to move forward talking about a reflex arc. A reflex arc has three parts. We have a sensory afferent fiber, an interneuron, or sometimes you'll see in a book or diagrams called association neurons, and then an alpha motor neuron. So we see over here, we have, if we touch something hot, we have a pain, a stimulus. Our afferent nerves, the sensory nerves, are going to bring information to the level of the spinal cord. A decision is going to be made at the interneuron level. Here it is named an association neuron, which is the same thing. And then it will tell us to retract our hand, move away from the hot object. That all occurs without higher order level of thinking. So before our brain has time to process that information, we have already moved our hand away from the flame or from the stove. You'll see the alpha motor neuron comes down to the muscle, and then we pull our hand away from the hot object. So three parts: sensory afferent, we sense the hot object. Interneuron decides what to do. Boom, we move our hand away. We send signals to that muscle, to certain muscles to contract and relax in order for us to bring our hand away from that object. Okay, so we're going to go through another reflex arc example a little bit more in depth. So for example, let's say we're going to stretch our quadriceps phasically. So that's very, very quickly, right? A phasic stretch is a quick stretch versus a tonic stretch, which is elongated over a period of time. So one, sensory. The type 1A fibers from the muscle spindles come into the gray matter of the spinal cord. At the same level that sensory input goes in, a signal must go out, right? A somatic efferent. So somatic, again, meaning to or from skeletal muscle, and efferent is going towards skeletal muscle or away. So we have that signal will cause that muscle to contract. So afferent, again, to recap, is going sensory from the muscle to the spinal cord and so forth, and then efferent is back to the muscle. And that signal will cause that muscle to contract, that somatic efferent. So also something that must happen at a different level. That signal will activate an interneuron, and that interneuron is going to impact on a motor neuron going in the opposite set of muscles, the hamstrings, which causes those muscles to relax. So let's go over that again. We're going to stretch the quadriceps phasically. So if we're going to stretch the quadriceps very quickly, we're going to have a reflex that's a protective mechanism. Our sensory input will be the type 1A fibers from the muscle spindles come into the gray matter of the spinal cord. At the same level that sensory input goes in, a signal must go out. So that somatic efferent, we're going to have those motor neurons going out to the muscle to tell it to do something. That signal will then cause that muscle, those quadriceps, to contract because, again, we don't want to stretch it too much. This is our protective mechanism. But at the same level, what's happening all of that at the quad, since we're stretching them phasically and then we need to contract them quickly in order for us to protect ourselves, something also has to happen on the level of the hamstrings. So that signal will also activate an interneuron, and that interneuron is going to impact on a motor neuron going to the opposite set of muscles, the hamstrings. So this is what's going to cause those sets of muscles to relax. So this total gives us all three parts. One, our sensory input. Two, our interneuron is going to induce relaxation or for the hamstring portion of this, and motor, two parts. One is to activate the quadriceps to contract, and one is to inhibit the hamstrings. So actually this reflex arc example is explaining both what happens at the level of the quadriceps and the hamstrings. Okay, so we're going to go over what a cross-extensor reflex is. This is considered a flexion reflex. This allows us to withdraw a body part from a threatening occurrence. So we're going to talk about something again like we just said about something hot, but we're going to talk about a cross-extensor reflex. So, for example, you put your hand on something hot, your muscles are going to flex and pull away, and the extensor muscles are going to relax. This will be processed at the level of the spinal cord, having some interneurons doing it once again. Most of the time, a flexion reflex is accompanied by an extensor reflex. So this means if you withdraw on one side, you will extend on the other side. So you'll pull back with your right arm and you'll extend your left arm to maintain balance. Another form of a cross-extensor reflex would be a projectile coming at you. The response would be to move your head away from it, but the eyes move in the opposite side to follow the object. So these are some examples of the cross-extensor reflexes that you may not even notice that you're doing, that your body automatically just does. So for example, when you pull away from the hot object, let's say you put your right hand on the stove, and you're going to flex and pull away and you're shifting your balance, automatically your left hand will start to extend. You may not notice it right away, or you may not even realize it after you take your hand off, because then your brain has realized, oh my gosh, my hand is burning and I got to go run it under cold water. But if you actually took time to notice that actually your body would automatically shift and your left arm or your left side of your body would extend a little bit as you pull your right hand away, because that is your reflex in order to maintain your balance. Another interesting one is if a projectile is coming at you, you move your head out of the way, but naturally a quick reflex is actually your eyes kind of follow the object. They go in the opposite direction to see where that object's going. Okay, so now that we talked about a reflex and certain things that are handled just at the level of the spinal cord, we're going to move on. We're going to talk about descending motor pathways, and this is controlled from higher brain centers. So the higher brain centers are controlled, they control of complex voluntary movements. So these higher brain centers must be involved. So versus a reflex where you just need to kick your leg out or pull your hand away from a flame very quickly, this requires a lot more control. For example, walking, locomotor patterns, and so forth. These require higher order level of thinking and control, which come from our higher brain centers. The spinal cord will be intimately involved because that's where the interneurons are, and that's where the alpha motor neurons are. But the decision that determines the contraction or relaxation is actually going to come from the brain, not from the spinal cord itself. So this means our spinal cord itself is under the control of 1, higher brain centers, and 2, the brain stem. Our higher brain centers are our cerebral cortex and our motor cortex. Those are the ones we're going to be talking about a lot. Right, so if you're going to talk about postural reflexes to keep us, upright and so forth, they're controlled in 2 locations. 1, our vestibular system, right? This wants to keep us upright, as well as our stretch receptors in the neck. So over here would be more specifically, a lot of these stretch receptors are located in our carotid sinus. Okay, so let's move on to locomotor patterns, because this requires higher level of thinking and control, so we need to talk about these higher brain centers. So ability to walk and run, for the most part, is controlled by locomotor centers of the brain. Complex voluntary movements are controlled by the pyramidal tracts. The pyramidal tracts include the corticobulbar tract and the corticospinal tract. So those are called the pyramidal tracts. Okay, so our pyramidal tracts, we're talking about efferent tracts here. These are upper motor neurons from the cerebral cortex and terminate either in the brainstem or in the spinal cord themselves. So let's talk about the corticobulbar tracts first. The corticobulbar tract conducts impulses from the brain to the cranial nerves. So that's important. These nerves control the muscles of the face and the neck and are involved in facial expression, mastication, swallowing, and other functions. So I'll say that again. The corticobulbar tract conducts impulses from the brain to the cranial nerves. These nerves are what control muscles of the face and neck are involved in facial expression. So in order for me to talk right now or chew or swallow or so forth, my corticobulbar tract is controlling that. So the next time you eat breakfast and you're allowed to chew and swallow, you can thank your corticobulbar tract for letting you do that. Sorry. And our next one is our corticospinal tracts. This is white matter. This is a white matter motor pathway starting at the cortex that terminates on motor neurons and interneurons within the spinal cord. So this controls movements of the limbs and trunk. There are more than 1 million neurons in the corticospinal tract, and they become myelinated usually within the first 2 years of life. So our corticospinal tract are going to be the ones that control our movement of our limbs and our trunk. So in order for you to put one foot in front of the other, or to dance, or to run, or to skip, or to jump, you can thank your cortical spinal tract, because those are the ones that are in control of those movements and cause those to move. Okay, so you can see with the diagrams different here, you can see the two different tracks. The blue here is the cortical bulbar tract, and then the red here is the cortical spinal tracts. And we're going to talk individually about these cortical spinal tracts in actually a little bit. We're going to get a little bit more depth into each of these cortical spinal tracts. But you can see blue here coming from the cortex. The cortical bulbar tract controls our face, tongue, and so forth. So facial expressions, chewing, swallowing comes down here, comes through the medulla, and ends here at the medulla and goes into the cranial nerves, which then control our face. And then here we have our hand, trunk, hip, knee, everything else is controlled by these cortical spinal tracts. So the cortical spinal tracts not only go through the brain, from the cortex, go through the medulla, they go down into some of them split, and we're going to talk about that. And they go into the spinal cord and deal with interneurons and then the alpha motor neurons in order to tell us what to do, to either put one foot in front of us, which muscles are going to contract and relax in order for us to move forward, or for us to stop, or to shuffle from side to side. So this is going to be the tract that tells us, that goes through the spinal cord and then gives the signals from the spinal cord to the sets of muscles of, okay, is this set of muscles going to contract and this is going to relax? So we can hopefully appreciate the speed of which all of this has to happen. And then last class we talked about everything that has to happen at the motor endpoint, where, you know, the once that signal goes down the alpha motor neuron, and the acetylcholine needs to be released and attached to the alpha receptors, and change the permeability on the other side, and go all the way down into release the calcium from the sarcoplasmic reticulum in order for it to bind to troponin, so we can shift out of the way, so we can contract. Now all of this comes up from up here, and we may take for granted just putting one foot in front of the other, or moving side to side, or moving our arm side to side. So this all has to happen, but it starts all up here actually, which is pretty crazy. Okay, so two other locations that actually help with complex motor activity we're going to just spend a slide on. This helps us regulate our complex motor activity, right? Because if we want to put one in front of the other, we also still need postural control. So one is our midbrain, and we're going to be mainly talking, that's pretty much the basal ganglia, and two is the cerebellum. So they don't initiate any motor activity specifically. These two areas don't necessarily initiate motor activity, but they make determinations of whether the motor program is going to be successful or not. So they modify movement on a minute-to-minute basis. So the output of the cerebellum to the cortex is excitatory, and the output of the basal ganglia is inhibitory. So together, they balance. They're a system of checks and balances for the most part. So these two systems make for a smooth, coordinated movement. All right. So once again, they don't initiate any motor activity specifically, but they make determinations. These are the systems that is going to determine, is this motor program going to be successful or not? They modify the movement on a minute-to-minute basis, so they are ultimately our systems of checks and balances if this motor program should be carried out or not, or is it doing so correctly? Again, the output of the cerebellum to the cortex is it's giving information to the cortex is excitatory, and the output of the basal ganglia is inhibitory. So those are the ones that are going to control what should we inhibit, what should we excite, what should we contract, what we could relax to, regarding the success of the motor program. Okay, so in our next video, we're going to continue this lecture with refined movements, and we're going to refer to our lateral muscles, and this is outside the gray matter, but we will continue how to control refined movements and then postural control next, and relate those to the different tracts of the cortical spinal tract.